Okay.
At the end of lunch, a kid threw milk at my backpack. It exploded on the ground. I cleaned up my bag, and then he walks by and cleans it up. Now he's complimenting us for keeping it.
A buffer solution contains 0.4 moles of formic acid and 0.6 moles of sodium formate in 1 liter of solution. Ionization constant is 1.48 times 10 to the minus 4. Calculate the pH of the solution. So A, how do we calculate the pH? We have what type of solution do we have here? A buffer. So we can use Henderson-Hasselbalch. So pH is equal to the negative log of our Ka, which is 1.8 times 10 to the minus 4, plus the log of our ion, 0.6 over our acid, 0.4.
Those are in moles.
Those are in moles, but it's in a 1 liter solution.
Is it a coincidence that they're all typically the Ks or Ks are like 1.8?
There's a lot of them that fall in that range, like formic acid and, but acetic acid is 1.8 times 10 to the negative 5, and ammonia is 1.8 times 10 to the negative 5. Yeah. Okay, so what'd y'all get for the pH? 3.92. All right, so there's part 1. The second part says if 100 mils of this buffer solution is diluted to a volume of 1 liter with pure water, the pH does not change. Why does the pH remain constant on dilution? The same ratio, yes. Because we diluted it equally. This ratio, 0.6 over 0.4, doesn't change. All right, C. 5 milliliter sample of 1 molar hydrochloric acid is added to 100 milliliters of the original buffer. Calculate the hydrogen ion concentration. So we have our acid, and it invades our buffer, and when it does, it's going to interact with our formate ion. And it's going to make formic acid. I'm using F for formic. So we need a mole table. So how many moles of H plus invades? So we have 5 milliliters and it's 1 molar, so 0.005 moles. How many moles are in our buffer? And it is 0.06. Because it's 1 molar, 100 milliliters, so we're only using 100 of the milliliters. So how many moles is in that 100 milliliters? So it's 0.06 moles. And we have 0.04 moles of our formic acid. So who's left standing? Who goes away in this war? H plus. So we subtract that from and add it to the next side. Huh? No, I'm subtracting it. So after the war, and we go and assess the damage, what's left? The weak acid and the ion. So what type of situation are we in? Henderson-Hasselbalch. So we use that to find our pH. pH is equal to the negative log of 1.8 times 10 to the negative 4th plus the log of our ion, 0.04 or 55 over, yeah, 0.045. 3.83 is our pH, and it wants to know what's the H concentration. So get the negative or 10 to the power of that.
1.48%.
And our unit is molarity. Everybody good with that? And lastly, 800 milliliters of our 2 molar fulvic acid is mixed with 200 milliliters of 4.8 molar sodium hydroxide. Calculate the H plus from this resulting solution. So now we're invaded with a hydroxide. So when we invade with our hydroxide, rather than the formate ion being used, we are using our formic acid to get water and our formate ion. How many moles are we invaded with? 4.8 molar, and it's 200 milliliters. 0.96? 0.96 moles, and we invade a 0.4 point. It's 1.6 moles.
Yeah.
And no formate ion. Hydroxide runs out first.
The 1.65, 2 molar, and then the 800 milliliters.
Yes. Sorry, that kind of just ran out of room right there. So after the war, what is left standing? Weak acid in the ion. So we calculate pH by using Henderson-Hasselbalch, negative log of 1 point.
Because it's a hydroxide, and most of the time we find the pH is correct.
0.96 over 0.64, and our pH is what?
How come the 0.96 went on top?
Because it's the ion.
But in the other one, in the other equation, oh, just kidding, never mind, I see it now, just kidding.
No, I have the same question. I have the same answer.
Huh?
Why aren't we using KB?
Why are we? Because we're using formic acid, because this is formic acid.
Then why can't we use KB in the other?
It doesn't matter what you're invading with. We don't care about what we're invading with.
But if
We
they
just care
had
about what's
acid,
left.
Hmm?
We just care about what's left.
We just care about what's being invaded. We're using the Ka for what's ever being invaded.
So if we were asked to find a concentration of hydroxide instead, would we have to find the KB value?
No, if it wanted to know hydroxide concentration, hydroxide, if it's a strong, then it wins.
Because they would only ask us that if it had been with a base. Okay, so it's not like that.
No. Now, if this would have been used, say, something else, some base, then we would have used Kb. But since we're using the formic acid, then we're going to use that Ka.
Okay, so if formic acid wasn't what we were using, so if we were using like NH3.
Yes, we would do Kb.
We just, okay.
Yes.
So the concentration is 1.2 times 10 to the negative.
So pay attention to what is being invaded, not what's doing the invasion. Thank you. Questions on that one? Okay, so what we're about to do is going to be tedious. I'm skipping question number 11. Well, I just want you to know in 11, you have a strong acid and it is invading a weak acid. So where's the pH going to come from? The strong acid. Ka doesn't matter. Who cares about the Ka? All right, so a quick tutorial or a quick overview of titrations. So if I were to take a titration and I were to look at the graph, and this is for a strong acid and a strong base, you need to know what your axes are labeled. You have your pH, and then you have your milliliters of, say this one we're going, how much base are we putting in? So this is what's in the burette. So if I have a strong acid and I titrate it, all a titration is an invasion. Okay? We're invading our acid with a base. Equivalence point in a strong acid, strong base is 7. And that is where what happens? Equilibrium? No. What is equal? Not concentration. The moles of the H plus is equal to the moles of the OH minus. Okay? I want you to know that the equivalence point is at 7 only for a strong acid, strong base. At anything else, it does not, equivalence point will not equal 7. No. Okay, so let's do some problems. Calculate, so a titration is performed by adding 0.6 molar KOH to 40 mils of 0.8 molar HCl. So we are invading HCl with OH. Calculate the pH before addition of any KOH. So we need to identify what type of acid we have. Strong. So we have a strong acid, and we are invading it with a strong base. So how do we find pH of a strong acid? So the H plus concentration is equal to the concentration of our HCl, right? Mm-hmm. And so we are going to say that the pH is equal to the negative log, and our concentration of HCl is 0.8. So our pH is what? 0.097. Okay, so this is what happens before we start the invasion. We're going to come back. Make sure these numbers are visible because we're going to come back and we're going to graph these numbers. All right, so let's start the invasion. Hydrochloric acid is invaded with our OH. And I'm just going to use the ions to give me water. We need the moles. We need to see who's going to run out first. So how many moles of OH did we invade with? 0.6 molar, but we put 20 mils in. So it is going to be 0.012 moles. How many moles of hydrogen are in our beaker? 0.8, and we have 40 mils. 0.032. This number is not going to change. That amount of moles in our beaker is always going to stay 0.032. And water goes away. So who is going to run out first? OH. So subtract it. And we're left with 0.02 moles of H plus. And we need to find pH. So we need to know how many milliliters do we have total in our beaker now. 60. So 0.06 is what we're going to divide this by. And that gives me what concentration for H plus? So 0.33 is our concentration of H plus. And now we use that to find pH. So we've added 20 milliliters, and what has our pH changed to? 0.48. Any questions on that? We're going to do this like 5 more times.
Yeah, I feel like would be 10 to the negative sign, or is it negative?
It's negative log, 0.33. All right. Well, we're still invading. Our whole purpose of a titration is to get to that equivalence point. So, and we are not there. So let's invade it. We're going to add some more. So again, we have our acid, and we invade it with our hydroxide to get us water. Our concentration of our acid, or our moles of our acid in that beaker, do not change. It is still 0.032. But now our hydroxide changed. Now we're at 40 and 0.4. 0.024. So hydroxide still runs out first. And we're left with 0.008 moles of H plus. I need to get that to molarity to find pH, so I'm going to divide it by the total amount in the beaker, which is how much now? 0.08 liters. So I have a molarity of 0.1. So what's our pH?
So it says the addition of 40, but it's
That's
actually
addition,
another 20.
another 20, yes. Our pH is 1. Still are not at equivalence point, so we're still invading. So acid is invaded with the hydroxide. Still have 0.032 that we're starting out with, but this time we have hydroxide 53 and a 0.6 molar. So it's 0.0318. Almost at equivalence point, but not quite there. So we still have to subtract hydroxide from both of them, and leaves me with 0.0002. 3 zeros? Is that right? Okay. So we are left with 0.0002 moles of H plus. And we need to get that to molarity. So how much is in our total, in our beaker now? 0.093. So our molarity is what?
Where are you getting that? Where did you get that number? Like, where did you get 0.0318 to?
.002. What did you say? Sorry.
So like, where'd you get .0318?
.0318. That's how much the moles of hydroxide that we added. So I know I added 53 mils of hydroxide, but in our molarity of our hydroxide is 0.6. So I need to know how many moles is that.
Oh, okay.
So I have
Okay.
0.6 times the .053.
Okay.
All right, so that is our H plus concentration. What's our pH? 2.7. Everybody good there? All right, going on. We want to know, what do we need to get to equivalence point? So H plus OH minus. How much H plus am I starting with? 0.032. So at equivalence point, how much OH do I need? 0.032 moles. So I want to know what's the volume? Oh, wait. Oh, crap. I went over too many, didn't I? Dang. Okay, here we go. So again, H plus OH minus H2O. We have 0.032 and 0.032 to get to equivalence point. What is our molarity of our OH? What's the molarity of the OH? I don't remember. Is it 0.6? 0.6. So let's find how many milliliters do we need to get there. So 0.6 molarity is equal to 0.032 moles over X amount of liters. Zero 0.533 liters, or 53.3 milliliters is needed.
So we were like almost there.
Almost there. Not quite. At equivalence point, what's the pH? 7. And why is it 7? Because it's a strong acid and a strong base.
So why does it start off like just barely? If all it is you have to have the same concentration, right? How come we
Not same concentration, same number of moles.
Why then when that just a little bit increases really slowly and then all of a sudden increases rapidly? Is there a reason for that?
It just doesn't take much to get there. It's just okay. So now let's go back to this one. Now we've added too much, and I want to see what our pH is after we've done that. So again, H plus OH minus gives me H2O. We still started out with 0.032 moles of hydrogen. How much hydroxide do we have now? So we've put 58.3 of our 0.6 molar. 0.035. So who's going to run out first this time is our hydrogen. And we're left 0.003 moles of our hydroxide. Huh?
I got 0.035.
Wait, from what? What are we talking about?
The molar volume.
The moles of OH is going to be at equivalence point. We were 53.3, and we've added 5 more past equivalence point. So we're at 58.3. Okay, everybody there now? All right, so we need to find pH. So what's our pOH? 0.031. So our pH, oh, wait. I skipped a point.
Yeah,
Part.
get them there.
We need to divide it by the milliliters. How many mils are in our beaker now? 0.0983. Right, because we had 24 plus or 40 plus the 58.3. So our OH concentration is 0.031. So our POH is 1.51, and our H plus is 12.49, or no, our pH. Sketch it. So pH is our Y, mils of OH is our X. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 5, 10, 15, 20, 25, 26, 27, 28. Okay, so our very first point is what? .97? 0.097? So it's like right there. Let me grab a different color. Right there. All right, our next is 0.481 after 20 milliliters. 5, 10, 15, 20. So after 40 milliliters, 5, 10, 15, 20, 25, 30, we're at 1. So we're not budging much. So 5, 10, 40, 50. At 53, we're at 2.67. So we're about right. 40, about right there.
What's that third?
Huh?
What's the third point in?
Third. So we have 0, 20, 40, 53. All right. Now, at equivalence point, where we would be at 7, that is at 53.3. So that would be about right there. And 5 over that, so 58.3. Is going to give me at 12.5. So if we were to connect these dots, we'll kind of look something like that. At 7, that is at pH 7, and right there, that is our equivalence point where our moles of H plus equal our moles of OH minus. Any questions on that? So either way, whether you're going acid into base or base invading acid, that is how you're going to do it. So now we're going to do a weak strong situation. So this time we have a weak acid being invaded by a strong base. And you need to know that RKA for Hochul is 3.5 times 10 to the minus 8. It's a weak acid because of the hydrogen,
There's not enough hydrogen.
but there's not, yes.
There needs to be more hydrogen.
There needs to be more O's. 2 or more O's, okay. Calculate the pH. So we need to know what the pH is before we start. So we have a weak acid. How do we calculate the pH of a weak acid? Nope. We don't have a buffer. We don't have the counterpart. So the rice table. So first thing we have to do is we have to add Hochul to water. We had Hochul to water, and we get Hochul minus and H3O plus. Our concentration of Hochul is 0.35. And we have minus X and plus X plus X. X is negligible. Not for me, but for the AP, I would put on there that it's negligible. All right, now we're ready to go into our K expression and set our Ka equal to our X squared, our products over our reactants. X, I find, is 1.11 times 10 to the minus 4, which is my H plus. So what's my pH? .96. Again, we're going to come back and graph this. All right, now we start the invasion. So Hochul gets invaded by hydroxide, and we get Hochul minus and water. It's an invasion, so now we need to go to Stoic and do a little mole table. So we need to know how many moles of Hochul are we starting out with. So we have 24 mils in a 0.35 molar solution. 0.0084. And we invade it with 5 mils of 2 molar sodium hydroxide. So that is 0.001 moles of sodium hydroxide. No Hochul, water goes away. So who's going to run out first? Hydroxide. So we subtract it from both sides and add 0.001 to the other. So after the invasion, what's left standing? Hochul and Hochul, which are conjugate acid and base. So we need to go into what to find pH? Henderson-Hasselbalch. pH is equal to the negative log of 3.5 times 10 to the minus 8 plus the log of our ion, 0.001, over our acid, 0.0074. So what is our pH? .59. We're going to do this 4 more times.
Today? Oh, not like 4 more of these whole problems.
Not 4 more of these whole problems, but this we're going to finish. I mean, we're going to do
the rest.
yeah. All right, everybody good? We're going again. Still invading, because our point of invading with a titration is to get our H and OH moles equal. So Hochul is invaded with hydroxide to give me Hochul minus, and water. Hochul's moles have not changed. But this time, hydroxide, the amount of moles, the moles of hydroxide that's in the solution is 15 times 0.2, so 0.003 moles.
We're just finding these moles by dilution, right?
By what?
Dilutions?
Mm-hmm. Not dilutions. The molarity times how many mils there are. Because molarity is moles per liter. And we know
Oh, okay.
how the concentration and we know how much is added. All right. Who runs out first this time? Again, is hydroxide. So it's subtracted from both sides, from the reactants and added to the products. And we're left with what type of situation? Henderson-Hasselbalch. So pH is equal to the negative log of 3.5 times 10 to the minus 8 plus the log of 0.003 over 0.0054. So what is our pH after we've added? Okay, that is a good question. Are we supposed to, so you want to get to molarity. They're both in the same thing, so the molarity, so they're both, what we divide each one of them by, the amount that we divide each one of them by is going to be the same, which means the ratio stays the same.
Right, so really the only time that we really have to divide back out to find molarity would be like if we were comparing in one beaker to another beaker.
Right. Okay, so the pH is 7.2. So, let's go again. We're still invading.
What's the equivalent point we're looking for?
Equivalence point is going to be where the moles of the acid equals the moles of the hydroxide.
Oh, okay.
So we got to get the moles of hydroxide to equal what we have in the beaker.
And the reason that this would be above or below 7 is just because it's a strong acid. There's like such big amount that it's going to looking at whatever pH the strong acid base is probably at, right? Does that make any sense?
Can you repeat that again?
Okay, so like compared to like maybe the strong acid and strong base, pH is the second, right? But it's the reason that it doesn't in this case would be that your strong acid or strong base is so much higher than you can.
Yes, it's going to overwhelm it. So we know at the end of this when at equivalence point, what, should we be basic or acidic? We're invading with a strong base, so we should be basic at equivalence point. Okay, so calculate the pH after addition of 25 mils. So again, Hochul is invaded by hydroxide to give me Hochul and water. Hochul is 0.0084 still. Hydroxide this time is 0.005. So our 0.005 is subtracted and added.
Where is that coming from?
Huh?
Where is the 0.005?
0.005. So it's 0.25 mils and it's 0.2 molar.
Why do we have to go through all of this work? Can we just go to the problem at the end and say, hey, this is the last one?
Because I want you to get practice.
I was just, if they give all of this in the AP test, we have to do every single problem.
No, they wouldn't give you something like this. This is you seeing it, being able to graph it out. Because usually we don't graph it out. What graphs it out for us?
The thing.
The lab quest. So this is you doing it, seeing where these calculations come from. This is what's happening within the computer. Okay.
Learning how to graph.
All right. So again, after the war, we're still left with our conjugate acid and base. So pH is equal to negative log 3.5 times 10 to the negative 8 plus the log of 0.005 over 0.0034. pH equals 7.62. Man, we're not going to get this before. So let's go again. Now we're adding 35 of the base. Alcohol and water. So again, we have 0.0084 of Hochul and of OH. This time we have 007. We subtract 007 from both sides, or from both, and then add it to the other side. 0.0014 and 0.007. We have to do this, yes. Huh?
That would be well deserved.
Negative log of 3.5 times 10 to the minus 8 plus the log of 0.007 over 0.0014. 8.15. So to get to equivalence point, what does OH have to equal? So we need OH to equal 0.0084 moles. And I want to know how much of that do I need to add so that I can get to equivalence point.
I feel like this problem shows up in the place where they're just done. Like, I could just do this.
What's the molarity of our base? 0.2. So how many milliliters do we need to get to equivalence point? 42 milliliters to get to equivalence point. Everybody good? Okay, so what I'm going to do is I'm going to stop here. Now tomorrow, when we get to, I have to show you guys what happens when you get to equivalence point, and after you go past equivalence point, and then we need to graph this. But you guys will have some homework tonight, so.